Okay, I'm going to start section 11.7 here, which is a strategy for testing series. Now that we've seen several ways to test a series, we want to now try to recognize which technique to use. Testing a series is similar to integrating functions in that there's no set of hard, fast rules to follow. It just depends on the type of series that you're wanting to see if it converges or diverges. Okay, so let's see. The first thing in section 11.7 is they kind of give us a strategy here, and so let's see. If I have just any series, and if I can see maybe at a glance that the limit as n approaches infinity of a sub n is not 0, then I know that the series diverges. That's the divergence test. Okay, don't forget about the divergence test. Okay, on some of these problems, the only way to do the problem is to use the divergence test. Okay, and then a p series is if you're in the form 1 over n to the p, or a geometric series is if you're in the form a times r to the n minus 1 or a times r to the n. Okay. We know the conditions for if a p series is convergent, that's if the p value is bigger than 1, and if a geometric series is convergent, that's if the absolute value of r is less than 1. Okay, the comparison tests can be used if you have something that that kind of maybe resembles like a p series or a geometric series, then I'd maybe consider a comparison test. Okay. Now remember that there's 2 tests for the comparison tests. Okay. There's the limit comparison test also. Okay, and that's kind of like a plan B option. You know, if the regular comparison test doesn't hold up true, then I'm using the limit comparison test. Okay, and I'm just checking to see if the limit is greater than 0. Okay, and the sequence that I was comparing it to, if the series is convergent, then the original series is convergent. If the series is divergent, then the original series is divergent. That's the limit comparison test. Okay, and then on the next page, alternating series test. Okay, so I think, you know, if you have anything involving a -1 to the n or a -1 to the n minus 1, like the first thing that I'm thinking of is obviously an alternating series. Okay, and so you know, the alternating series test can be used. Okay, now sometimes the alternating series test is best tested with the ratio test. Okay, it says that series involving factorials or products raised to the nth power are used primarily with the ratio test. Okay, because you'll be able to get, you know, things canceling out there. Okay, and then there's the root test. Okay, the root test out of all these tests is probably the least used. Okay, because really the only time that I consider using the ratio the root test is if I'm in the form of b to the n to the nth power. Okay, if I got some series raised to the nth power, then if I take the nth root, that's going to get rid of the nth power there. Okay, that's the only time that I'd consider using the root test. And then there's also the integral test. Okay, now if you can see at a glance that the sequence, it looks like it would belong in an integral, then you can consider using the integral test. Okay, but remember with the integral test, there's 3 conditions that have to happen first though before you use the test. Okay, so you have to have a positive function. It's got to be continuous and it's got to be decreasing. Okay, if those 3 conditions are satisfied, then yeah, you can use the integral test there. Okay, and so they give you some examples in this section, and then there's the problems in this section. Okay, So maybe why don't we? I think that the best thing to do here is just to take a look at some ordinary, series and just check if they converge or diverge, in no particular order. Okay. So what if we had this summation as k equals 1 to infinity of k times k plus 2 divided by k plus 3 squared? Well, okay, so let's see. If I were to use a comparison test on this, if I didn't have the plus 2k up top, then I'd have k squared. And if I didn't have the plus 3 in the denominator, I'd have k squared. There. K squared over k squared is 1. Well, 1. Okay, well, I'm not getting 0, right? So I guess the next thing that I'd want to think of is maybe this is a divergence test type situation. Okay, so if the limit as k approaches infinity of the sequence k squared plus 2k divided by k squared plus 6k plus 9 is not 0, then I know that the series diverges. Okay, well, let's see. I'm going to go ahead and multiply the top and bottom by 1 over k squared, and then distribute. Or I could use L'Hopital's rule, same thing. But if I distribute 1 over k squared, both in the numerator and denominator, I'm going to have the limit as k approaches infinity of 1 plus 2k divided by 1 plus 6 over k plus 9 over k squared. Okay, these three terms here are going to go to 0 as k is approaching infinity, and so I get 1 over 1 is 1. Well, 1 is not 0, right? So that tells me that I know that this series is going to be divergent because of the divergence test. Okay, and usually you say what test you're going to use. When you say if a series is convergent or divergent, you say it diverges by the divergence test, or it converges by the comparison test, or whatever. Okay. Now, another thing to know is that usually with these problems, there's only one way to do the problem. Okay. Same thing with integral problems. There's usually only one way to do the problem. Okay. Sometimes not. Okay, but consider that. And if one test doesn't work, like the comparison test didn't work here, then try another test, okay, and see if it works for that one. Okay. Here's another example. So what if I had the summation as n equals 2 to infinity of 1 divided by n times the square root of n squared minus 1. I'm going to start at 2, not 1, because of the denominator 1 minus 1 is 0. Okay, so I can't divide by 0, right? So that's why I'm starting at 2. Okay, now this looks like a comparison test situation. Okay, so if I were to compare this to like what if I did not have the minus 1 underneath the square root sign? Okay, I'm comparing 1 divided by n times the square root of n squared minus 1 with 1 divided by n times the square root of n squared. Okay, well, if I'm subtracting 1 in the denominator, then that's going to make the overall denominator on the right a bigger number than the one on the left. Okay, so the corresponding fraction on the right side would be a smaller number with that bigger denominator than the one on the left. Okay. Now 1 divided by n times the square root of n squared, that's the same as 1 divided by n times n is n squared. It's like a 1 over n squared. Okay. This statement here is true for all n that's greater than or equal to 2. Okay, now this comparison is useless though. It doesn't help me, right? Because I know that this is a p series. If I had the summation as n equals 2 to infinity of 1 over n squared, that would be a convergent p series. Okay, and now I'm comparing that to something that where term by term is bigger. Okay, so how do you know that the original series doesn't diverge? It could diverge. Okay, so this comparison doesn't work for us. Well, the next thing is I'm going to stick with the comparison test, but I'm going to use the limit comparison test. Okay, think of the limit comparison test as like a plan B option for like if the if the comparison test, the standard one, didn't work out. Okay, so a sub n is 1 divided by n times the square root of n squared minus 1, and b sub n is 1 over n squared. Okay, so I got the limit as n approaches infinity of a sub n divided by b sub n. Now all I'm looking for is if this limit calculation is some number that's bigger than 0. If it is, then I'm comparing it to a convergent p series, and I know that the original series would converge. Okay, so I got the limit as n approaches infinity of 1 divided by n times the square root of n squared minus 1 divided by 1 over n squared. If I flip the denominator, n squared over n, that's n, and then now I'd still be an indeterminate form here, okay, infinity over infinity. I'm going to go ahead and multiply the top and bottom by 1 over the square root of n squared, which is 1 over n. But so I've got the limit as n approaches infinity of n divided by the square root of n squared minus 1 times 1 over the square root of n squared divided by 1 over the square root of n squared. And the square root of n squared is n, so n over n is 1 up top. And I'm going to go ahead and keep the radical notation down under. So I got the square root of n squared minus 1 divided by the square root of n squared. That would be the square root of n squared minus 1 divided by n squared. Okay, and underneath the square root sign, let me go ahead and split up that one fraction there into two fractions. So n squared minus 1 over n squared, that's the same as 1 minus 1 over n squared. The reason for doing that is because now I can find the limit as n approaches infinity. So the limit as n approaches infinity of 1 over n squared, that's 0. 1 over the square root of 1 is 1, and 1 is a positive number. That's all I was looking for here, right? So that was getting a positive number. Okay, that's a positive number. And the sum is n equals 2 to infinity of b sub n. That's a convergent p series, like I said. So because that converges, I know that the original series is also going to converge. Okay? And that's going to happen by the limit comparison test. Here's another one. So we have the summation as n equals 1 to infinity of n times e to the negative n squared. Okay, well, that looks like it would belong in an integral. If I had, if I were integrating x times e to the negative x squared, that would be just a simple u substitution. Okay, now, so I think I can use the integral test here. Now I got to verify that there's 3 conditions to use the integral test. I don't want to just blindly set up an integral and start integrating it. That doesn't tell me anything, right? I need to make sure I can use the test. So I'm checking for 3 things, okay? The first thing is that n times e to the negative n squared has to be positive. Well, I'm positive everywhere, right? So n times e to the negative n squared, that's also going to be positive. And I need to be continuous on the integral 1 to infinity. Well, n divided by e to the n squared, that's going to be continuous everywhere, right? There's no numbers that would create 0 in the denominator. Okay, so then the only other thing I'm checking for is that the terms decrease. Okay, well, let me go back to Calc 1 here, and we'll use the first derivative test. So if f of x is x divided by e to the x squared, f prime of x will be using the quotient rule. I'm going to have the bottom e to the x squared times the derivative of the top is 1 minus the top x times the derivative of the bottom. That's be a chain rule. That'd be e to the x squared times the derivative of x squared is 2x divided by the denominator squared. Okay, e to the x squared is in common of these two terms here. So let's go ahead and factor that out. And I can cancel that with one of the e to the x squared terms in the denominator. Okay, so that's gone. And I'm left with 1 minus 2x squared divided by e to the divided by e to the x squared. Now I need to know when that's less than 0 because I need to know when these terms are decreasing. Well, the denominator is always going to be positive, no matter what. Okay, so I just need to know when the numerator is going to be less than 0. Okay, well, if I solve this inequality, let's add 2x squared and then divide by 2. I get x squared greater than 1/2, and then take the square root of both sides. So you have x is greater than 1 over the square root of 2. Okay, well, 1 over root 2 would be about 0.707. So yeah, you're going to be decreasing on the entire interval 1 to infinity. Okay, so I can use the integral test here, in other words. Well, if I use that test, I got the integral going from 1 to infinity of x times e to the negative x squared dx. And that is the limit as t approaches infinity of the integral going from 1 to t of x times e to the negative x squared dx. So remember that it's an improper integral. Yeah, it's going to be a u substitution. So if I let u be negative x squared, du would be negative 2x dx. And I've got an x dx in the integral. So I'm going to have to bring out a negative 1/2 there. And that negative 1/2 can also come outside the limit. So I'm going to have negative 1/2 times the limit as t approaches infinity of the integral going from, let's see, when x is 1, u is negative 1. And when x is t, u would be negative t squared. And I'm integrating e to the u du. Okay? Now, let's see. The bounds don't make any sense here because I'm approaching infinity. So I'm going from negative 1 to negative infinity. No. The upper bound always has to be the bigger number. Okay? So I want to switch the bounds. And by switching the bounds, I got to throw a negative in front. So I'm going to have 1/2 times the limit as t approaches infinity of the integral going from negative t squared to negative 1 of e to the u du. Okay, and that's going to be 1/2 times the limit as t approaches infinity of e to the u, which is being evaluated from negative t squared to negative 1. So then when I plug in the bounds, I get 1/2 times the limit as t approaches infinity of e to the negative 1 minus e to the negative t squared. Okay, the limit as t approaches infinity of e to the negative t squared, or 1 over e to the t squared, that'd be 0. Okay, e to the negative first is 1 over e. The limit of a constant is always the constant. So I'm going to have 1/2 times 1 over e, that's 1 over 2e. And that's a finite number. So the integral converges. And that tells me that the series is also going to converge. Okay, now remember that I don't know if the series converges to 1 over 2e. It doesn't, by the way. But I only know that it converges. Okay, so I'm using the integral test there. Okay. All right, we'll go ahead and stop right here in this video. I've got a couple more examples. I'll show you those in the next video.